Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about introduction to destructive and non-destructive testing and its classification. In this lecture video, I will discuss upon acoustic emission technique, AET. So let's get started. The content of this lecture video is as follows. I will discuss about acoustic emission technique in detail, followed by I will discuss about AE testing methods, a brief history of AE testing, AE sources, the equipment of acoustic emission testing, and the applications of acoustic emission techniques. Acoustic emission testing is a non-destructive testing technique that detects and monitors the release of ultrasonic stress waves from localized sources when a material deforms under stress. Now let's see how does it works. Acoustic emission testing works by mounting small sensors onto a component under test as shown in this diagram. The sensors convert the stress waves into electrical signals, which are relayed to a acquisition PC for processing. The waves are captured when the component is submitted to an external stimulus, such as high pressures, loads, or temperatures. As the damage grows in the component, there is a greater release of energy. The rates in which the acoustic emission is detected, the activity and the intensity of the acoustic emission, the loudness, and the monitored and used for assessing structural integrity and for health monitoring of components. Acoustic emission can be thought of as tiny earthquakes that occurs in the material. The technique globally monitors a component of defects, allowing large structures and machines to be monitored while in operation with minimal disruption, unlike destructive testing. By using multiple sensors, acoustic emission sources, and hence the damage can be located. Through signal analysis, the presence of different source mechanisms can also be determined. Acoustic emission is an amazing, promising, and challenging subject of the modern technology and science. It is a well-known from everyday life phenomena. Sound of breaking glass, falling trees, cracking ice are some examples of fracture sound we may hear from different objects subjected to stress. Scientifically defined, acoustic emission is a phenomenon of sound and ultrasound wave generation by materials that undergo deformation and fracture processes as shown in this figure. Sources generated acoustic emission in different materials are unique. For example, in metals, primary macroscopic sources are crack jumps, processes related to plastic deformation development and fracturing and debonding of inclusions. Quantitative and qualitative characteristics of acoustic emission waves generated by sources of different nature depend directly on material properties and environmental factors. Piping inspection in another common application. Acoustic emission is used efficiently and fast for detecting of cracks, corrosion damage, and leaks. There are multiple advantages of the method in case of piping inspection. For example, in case of buried or insulated pipelines, as shown in this figure, there is no need to open the entire surface of the pipe and just a small opening of installation of sensors, while a distance between sensors can be from few meters to 100 meters. Acoustic emission testing is applied also for inspection of high pressure and temperature piping systems during their normal operations. As shown in this figure, acoustic emission sources related to corrosion development and a leak in an underground pipeline is shown. The calculation of acoustic emission source location based on the detected time difference between waves arrival to sensors and known wave velocities are shown in this diagram. The distance between two acoustic emission sensors is capital D, whereas the distance from the sensors and the flaw is a small d. Therefore, we can write the small d, that is the location of the flaw, and the sensor, that is small d, is equal to half into capital D minus delta T into capital V. In this equation, small d is the distance from first hit sensor, capital D is the distance between sensors, capital V is the wave velocity, and delta T is the time difference between transmitted and received waves. Now let's see the types of AE testing methods. There are two AE testing methods. One is transient and second one is continuous. So first of all, let's see what is the transient method. The transient acoustic emission method captures AE burst that exceeds a threshold, that is loudness level, and they extract features such as peak amplitude, signal energy and duration of the burst. These features are then used to assess the condition of the component under test. This method is well suited for testing structures for defects such as cracks. Second AE testing method is continuous method. The continuous method captures all AE within a set time period, for example 1/10 of a second. Then features such as average signal level and root mean square, that is RMS value, are then extracted. This method is well suited to applications where there is a lot of background AE or AE amplitude is low. For example, when testing gearboxes or detecting leaks. Acoustic emission testings can be conducted in a laboratory as well as in field conditions. Over both relatively short durations such as few hours and longer durations such as few months, wireless data relay methods make it possible to analyze the data remotely. Now let's see a brief history of acoustic emission testing. Although acoustic emissions can be created in a controlled environment, they can also occur naturally. Therefore, as a means of quality control, the origin of AE is hard to pinpoint. As early as 6500 BC, potters were known to listen for audible sounds during the cooling of their ceramics, signifying structural failure. In metalworking, the term tin cry, audible emissions produced by the mechanical twinning of pure tin during plastic deformation, was coined around 3700 BC by tin smelters in Asia Minor. The first documented observations of AE appear to have been made in 8th century by Arabian alchemist Jabir ibn Hayyan. In a book, Hayyan wrote that Jupiter, that is tin, gives off a harsh sound when worked, while Mars, iron, sounds much during forging. Now let's see acoustic emission sources. Acoustic emissions can result from the initiation and growth of cracks, slip and dislocation movements, twinning, or phase transformation in metals. In any case, AEs originate with stress. When a stress is exerted on a material, a strain is induced in the material as well. Depending on the magnitude of the stress and the properties of the material, an object may return to its original dimensions or be permanently deformed after the stress is removed. These two conditions are known as elastic and plastic deformation respectively. The most detectable acoustic emissions takes place when a loaded material undergoes plastic deformation or when a material is loaded at or near its yield stress. On the microscopic level, as plastic deformation occurs, atomic planes slip past each other through the movement of dislocations. These atomic scale deformations release energy in the form of elastic waves, which can be thought of as naturally generated ultrasound traveling through the object. When cracks exist in a metal, the stress levels present in front of the crack tip can be several times higher than the surrounding sound. Therefore, AE activity will also be observed when the material ahead of the crack tip undergoes plastic deformation, that is micro-yielding. Acoustic emission testing can be performed in the field with portable instruments or in a stationary laboratory settings as shown in this figure. Typically, systems contain a sensor, preamplifier, filter, and amplifier along with the measurement, display, and storage equipment, that is oscilloscopes, voltmeters, and personal computers. Acoustic emission sensors respond to dynamic motion that is caused by an AE event. This is achieved through transducers which convert mechanical movement into an electrical voltage signal. The transducer element in an acoustic emission sensor is almost always a piezoelectric crystal, which is commonly made from a ceramic such as lead zirconate titanate, that is PZT. Transducers are selected based on operating frequency, sensitivity, and environmental characteristics and are grouped into two classes, resonant and broadband. The majority of AE equipment is responsive to movement in its typical operation frequency range of 30 kHz to 1 MHz. For materials with high attenuation, that is plastic composites, lower frequencies may be used to better distinguish AE signals. A schematic diagram of a basic acoustic emission testing system is shown in this diagram. Ideally, the AI signal that reaches the mainframe will be free of background noise and electromagnetic interference. Unfortunately, this is not realistic. However, sensors and preamplifiers are designed to help eliminate unwanted signals. First, the preamplifier boosts the voltage to provide gain and cable drive capability. To minimize interference, a preamplifier is placed close to the transducer. In fact, many transducers today are equipped with integrated preamplifiers. Next, the signal is relayed to a bandpass filter for elimination of low frequencies common to background noise and high frequencies. After completion of this process, the signal travels to the acoustic system mainframe and eventually to a computer or similar device for analysis and storage. Depending on noise conditions, further filtering of amplification at a mainframe may still be necessary. After passing the AE system mainframe, the signal comes to a detection or measurement circuit as shown in figure. Note that multiple measurement circuits can be used in multiple sensors or channel systems for source location purposes. At the measurement of circuitry, the shape of conditioned signal is compared with the threshold voltage value that has been programmed by the operator. Signals are either continuous, that is analogous to Gaussian, random noise with amplitudes varying according to the magnitude of the AE events, or burst type. Each time the threshold voltage is exceeded, the measurement circuit releases a digital pulse. The first pulse is used to signify the beginning of a hit. A hit is used to describe the AE event that is detected by a particular sensor. One AE event can cause a system with numerous channels to record multiple hits. Pulses will continue to be generated while the signal exceeds the threshold voltage. Once this process has stopped for predetermined amount of time, the hit is finished as far as the circuitry is concerned. The data from the hit is then read into a microcomputer and the measurement circuit is reset. Now let's see the applications of acoustic emission technique. Acoustic emission is a very versatile, non-invasive way to gather information about a material or structure. Acoustic emission testing is be applied to inspect and monitor pipelines, pressure vessels, storage tanks, bridges, aircraft, and bucket trucks, and a variety of composite and ceramic components. It is also used in process control applications such as monitoring welding processes. A few examples of AE applications are as follows. First of all, welding monitoring. During the welding process, temperature changes induce stresses between the weld and the base metal. These stresses are often relieved by heat treating the weld. However, in some cases, tempering the weld is not possible and minor cracking occurs. Amazingly, cracking can continue for up to 10 days after the weld has been completed. Using stainless steel welds with known inclusions and accelerometers for detection purposes and background noise monitoring. It was found by W.D. Jolly in 1969 that low-level signals and more sizable bursts were related to the growth of microfissures and larger cracks respectively. A standard practice of AE monitoring of continuous welding is shown in this picture. Next application is bucket truck integrity evaluation. Accidents, overloads, and fatigue can all occur when operating bucket truck or other aerial equipment. If a mechanical or structural defect is ignored, serious injury or fatality can result. In 1976, the Georgia Power Company pioneered the aerial manlift device inspection. Testing by independent labs and electrical utilities followed. Although originally intended to examine only the boom sections, the method is now used for inspecting the pedestal, pins, and various other components. Normally, the AE tests are second in a chain of inspections which starts with visual checks. If necessary, follow-up tests take the form of magnetic particle, dye penetrant, or ultrasonic inspections. Experienced personnel can perform 5 to 10 tests per day, saving valuable time and money along with the way. The procedures for examining insulated aerial personal devices is shown in this picture. Next application is gas trailer tubes. Acoustic emission testing on pressurized jumbo tube trailers was authorized by the Department of Transportation in 1983. Instead of using hydrostatic retestings, where tubes must be removed from the service and deassembled, acoustic emission technique allows for in-depth testing. A 10% overpressurization is performed at a normal filling station with AE sensors attached to the tubes at each end. A multi-channel acoustic system is used to detect and map to source locations. Suspect locations are further evaluated using ultrasonic inspection, and when defects are confirmed, the tube is removed from use. Acoustic emission technique can detect subcritical flaws, whereas hydrostatic testing cannot detect cracks until they cause rupture of the tube. Because of the high stresses in the circumferential direction of the tubes, tests are geared towards finding longitudinal fatigue cracks. Next application of acoustic emission technique is in bridges. Bridges contain many welds, joints, and connections, and a combination of load and environmental factors heavily influence damage mechanisms such as fatigue, cracking, and metal thinning due to corrosion. Bridges receive a visual inspection about every 2 years, and when damage is detected, the bridge is either shut down, its weight capacity is lowered, or it is singled out for more frequent monitoring. Acoustic emission is increasingly being used for bridge monitoring applications because it can continuously gather data and detect changes that may be due to damage without requiring lane closures or bridge shutdown. In fact, traffic flow is commonly used to load or stretch the bridge for AE testing. Next application of acoustic emission technique is in aerospace structures. Most aerospace structures consist of complex assemblies of components that have been designed to carry significant loads while being as light as possible. This combination of requirements leads to many parts that can tolerate only a minor amount of damage before failing. This fact makes detection of damage extremely important, but components are often packed tightly together, making access for inspections difficult. Acoustic emission technique has found applications in monitoring the health of aerospace structures because sensors can be attached in easily accessed areas that are remotely located from damage-prone sites. Acoustic emission technique has been used in laboratory structural tests as well as in flight test applications. NASA's Wing Leading Edge Impact Detection System is partially based on AE technology. The image to the right shows a technician applying AE transducers on the inside of the Space Shuttle Discovery wing structure. The impact detection system was developed to alert NASA's officials to events such as the sprayed on foam insulation impact that damaged the Space Shuttle Columbia's wing leading edge during launch and led to its breakup on re-entry to Earth's atmosphere. There are several other applications of acoustic emission techniques, which are fiber reinforced polymer matrix composites, in particular glass fiber reinforced parts or structures, example fan blades. Material research, for example, investigation of material properties, breakdown mechanisms, and damage behavior. Next is inspection of quality assurance, example, wood drying processes, scratch tests. Next is real-time leakage test and location within various components such as small valves, steam lines, tank bottoms. Next is detection and location of high voltage partial discharges in transformers. Next is railroad tank car and rocket motor testings. Now let's see the advantages of acoustic emission techniques. The ability to detect a range of damage mechanisms including fire breakages, friction, impacts, cracking, delamination and corrosion in their early stages before they become significant issues. It can be conducted during operation, during qualification testing or during development testing. It can locate damage sources and can be differentiate these based on acoustic signatures. It is global monitoring of a structure. The assessment of the structure or machine under real operationals can be done. The operational in hazardous environments including high temperatures, high pressures and corrosive and nuclear environments also can be done with the help of this testing method. It can be conducted remotely and it can detect damages in defects that are difficult to access with conventional non-destructive testing techniques. Now let's see few limitations of acoustic emission technique. Limited to accessing structural integrity or machine health by locating issues, further inspection is usually required to fully diagnose issues. It cannot detect defects that may be present but that do not move or grow. It can be slower than other NDT techniques. So these are the several limitations of acoustic emission technique. This is all about acoustic emission technique. In my next lecture video, I will discuss about radiography testing, that is X-rays or gamma rays, and ultrasonic testing. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.